Hi everyone, my name is Ndabenhle from the University of KwaZulu-Natal, and my topic today is paleoclimate. Okay, so far you've heard about the distance of the Earth relative to the Sun, and also you've heard about excuse me, you've heard about the greenhouse effect, which is might be the reason why the Earth is so habitable. And again, you've heard about the atmospheric circulation, which is weather and climate. And in the hierarchy of models, we are here, which is number 4. And I'm going to be talking about the climate and past climate, and we're going to try and see or predict what the future climate might be. In my presentation today, you're going to be seeing a lot of this slide over here, which tells us about the average temperatures over time, but then they only show us the averages from 6 million years ago. At the end of this presentation, you're going to be able to understand why do we care, why do we need to study paleoclimate, and you're going to be able to understand how do we know about the distant past, because obviously we can't travel back in time, and you're going to be able to understand what the records tell us about past climate and the predictions about the future climate. In our introduction, firstly we need to understand what is climate. Climate is persistent weather conditions over a prolonged period of time, and paleo simply means past, or one would say ancient. So paleoclimate, it is the past climate, and paleoclimatology, it is the study of paleoclimate. Why study paleoclimate, one would ask. But then it is very important to understand the past. So we need to understand the past through the present. So present is key to the past. So we need to understand how the climate was a long period of time, and we need to be able to predict what the future holds, or what the future climate might be, so that we can be prepared for the future. And with the present telling us about the past, we can be able to predict what the future might be, so we can develop theories and we can build models to try and explain all this. So paleoclimatic data can be gathered or can be obtained using two different types. We have indirect climatic data and direct climatic data. Or in indirect climatic data, it is recorded, okay, maybe it was used before 1850, and direct climatic data, it was used after 1850. So till today we use the direct climatic data. I'm going to try and explain the difference between the two in the next slide. Okay, here I have examples of paleoproxies. What are paleoproxies? Paleoproxies are simply the remains of the remains of the past climate. So here we can see we have ice cores, we have coral reefs, we have tree rings, we have ocean and lake sediments. Under ice cores, sorry about this. Ice cores are these, where scientists drill down the ice. They take out the ice, that is the ice edges. So in these ice cores, we look at the things that might be trapped inside the ice. Things might be dust particles, or it can be carbon dioxide. It can also be different things, because the climate changes over time. So what's inside there can help us conclude what the climate was at that period of time. With the coral reefs, well, inside the shells we can use a microscope, or I can easily say in a laboratory we can find out the chemical composition of these shells, so that we can see what the climate was at that period of time. When it comes to tree rings, it is slightly different from the two above that I've mentioned. The tree rings tell us about the average rainfalls in that year, because each ring represents 1 year. So in that ring, if you measure the ring, the thickness of the ring, it tells us the amount of rainfall which we received in that year. So if the ring is thicker, well, that means we received a lot of rainfall in that period of time. If the ring is thin, we received less rainfall. With that, we can again mention how the climate was at that period of time. Ocean and lake sediments. Ocean and lake sediments are similar to the coral reefs, because we also go to the lab to try and analyze what the compositions of these sediments tell us about the past climate. So paleoproxies fall under indirect climatic data, because we use what we see now to indirectly see what the climate was in that period of time. Methods of dating. Well, when it comes to dating, well, one would say it's when a guy takes out a girl, or it's when two people, when a guy and a girl go out for a date. But then here we have relative dating and absolute dating, and the difference between the two is that relative dating is when relative dating doesn't tell you the specific age of an organism, but then absolute dating tells you the exact age of the organism. If you look at this diagram here, which shows us the young and old sediments, this organism here, this organism here, it is found in the middle of these sediments. So the sediments here at the bottom are older than the ones at the top. So this organism here, it is younger, or it is older than the sediments it is younger than the sediments in the bottom. That is relative dating. When it comes to radiometric dating, it uses isotopes. Okay, the examples for this, it is radiocarbon dating and potassium argon dating. Well, when it comes to radiocarbon dating, it is whereby, well, we all know that if a living organism takes in carbon dioxide, well, carbon 14, but then as it dies or as it passes on, it stops to take in this element. So from then it stops taking in, so it is only giving out carbon 14. Be able to predict how long the organism has died. So that is radiometric dating. Okay, we see this diagram again, and here I'm showing it because I'm gonna try and explain why from 3 million years ago the average weather temperatures are fluctuating too much when compared to before 3 million years, which is here. With that, I have Milankovitch cycles. These cycles were explained by the scientist or the mathematician named Milankovitch. Well, here I'm gonna show you a demonstration. I hope it's gonna play. I'm gonna show you a demonstration to show you this. I'm sorry about that. Okay, please respond. Okay, I'm gonna show you a demonstration in order for you guys to easily understand what I'm talking about when I'm talking about the Milankovitch cycle. First of all, we have eccentricity. Eccentricity, it is well, it is well known because most people are aware that the Earth rotates around the sun. It is not the sun that rotates around the Earth, giving us the night and day. Okay, let's see how this come about. When it comes to eccentricity, we know that the Earth rotates around the sun, as you can see here. It rotates around the sun, but then as time goes on, the motion or the shape of the rotation, it changes as time goes on. It changes, and it changes from being circular to elliptical. As you can see here, it is starting to be elliptical, and this cycle, okay, one cycle takes a period of approximately 1,000 years. So we're not going to be able to experience this, because we only live up to maybe 100 years if we are lucky. Like me, I'm going to live like 100 years or 120 years. But then still, I'm not going to be able to experience this cycle. See here the shape, it has changed. It is now elliptical. But then the next one, it is, okay, sorry about that. It is called the tilt. The tilt basically tells us that the Earth, as it rotates around the Sun, it is not straight like this, but then it is tilted like this at an angle of 23.5 degrees, but then it is well known as 24 degrees. This, it only lasts about also a few thousand years, and again we're not going to be able to experience this. So as you can see here, it is tilted 23 degrees. I hope everyone can see that, giving us summer and winter. The next one is precision. Precision basically is that well, the Earth rotates around as it rotates, it gives us elliptical shape as it rotates, but then it is tilted like this. It is not straight like this. It is tilted like this. As it is tilted, it wobbles like this, like a spin top. It wobbles like this. It goes like this, but it wobbles, which is right here. I hope it's gonna be clear. It wobbles like this, like a spin top, and this only lasts about 25,000 years. I hope that was clear. I'm gonna go back to my slides. So the Milankovitch cycles give us the tidal and intertidal periods, whereby we have a lot of ice, and we lose ice, and it gives us summer and winter. And at the end, this is the overall graph of these cycles, whereby we have E, which is eccentricity, the rotation, it becomes more elliptical. T, which is the tilt, it is tilted 23.5 degrees. P, which is precision, it wobbles as it goes around the Sun. I hope this is very clear. And the big question here is, are we moving towards the fireball Earth? Because, well, a long time ago we know that it was called a snowball Earth. A snowball Earth, whereby the Earth was surrounded by the ice, and temperatures started increasing as the time went on. But then you see here, they are increasing at a very alarming rate. So are we approaching a fireball Earth? Just here, as you can see, as the average carbon dioxide, they are increasing rather. So are we reaching for this? Should we worry? What's gonna happen? And this brings us to, why is South Africa special? If you look here, we have diamectites and stromatolites. These were found, the diamectites were found in Klerksdorp, and the stromatolites were found in the Port Elizabeth. These carry a lot of information about the paleoclimate, and we are so happy that with these we can be able to see what the climate was in South Africa. And yes, with the sediments trapped inside here, we can be able to date and be able to see what the climate was a long time ago. And in our summary, I hope in this lecture you were able to find out the term weather patterns, future climate can be predicted